Welcome to central tendency. When we're talking about a set of scores, whether it be a sample or a population, we're talking about trying to find the middle. A good way to talk about where is the middle of a set of scores. And as you might guess, we have one way, usually the mean, that we'd like to use for a number of reasons that we'll get into. But sometimes the mean is not appropriate depending on the distribution of our scores, the presence of outliers, the extremity of the outliers. So we'll also have to learn about some other measures of central tendency. The others you probably heard about too. So in this coverage of this concept, we probably won't get into anything that's super new territory for you. But again, we're starting slow as we build up some of the foundational pieces of the more complicated statistics that we're going to do later in the semester. Let's do a quick review of Chapter 2, followed by discussing the goals of central tendency, the pros and cons, the advantages, the limitations, the three different kinds of central tendency, as you can see, why we'd want to pick one, and particularly the situations in which one would be desirable over the others, and putting them all together and looking at them in terms of the shape of distributions. But first, a review of Chapter 2. This is our different ways of displaying data. Difference between a frequency histogram and a bar graph is the bar graph will be used to represent discrete data, either categorical or ordinal, whereas the histogram will be used to represent continuous data, either interval or ratio. And the difference between a histogram and a polygon, they look a little bit different in terms of whether it's bars or whether it's dots that are connected, but they represent the same kind of data. Proportions and percentages are similar in that they represent the same thing, except a proportion is a decimal that just is converted into a percentage. Symmetrical distributions, remember, if we cut it down the middle and fold it over, they line up exactly, whereas skewed means scores are bunched more on the left or right-hand side of the distribution. When scores are bunched up in a negatively skewed distribution, they are bunched up on the right side because that will pull the mean away from the peak of the distribution. The exact opposite is for a positively skewed distribution where the peak is on the left side, but the outliers will pull the mean in the right-handed or positive direction. Remember, sometimes they might look similar in terms of how we present the data, but it's always important conceptually to think about what are we doing. We'd like to have population data, which is all the potential scores that we care about. Usually we're stuck with a sample. And we have a quick symbol review as well. F involves frequency. We can have the frequency of an individual score, or we can have cumulative frequencies that as we move up from x equals 1 to x equals 2, not just how many scores of a particular value do we have, how many scores of a value at that value or below, cumulatively for all values of that value or below. Now let's transition into central tendency. First, we want to have one number that represents an entire distribution, and most specifically, some sort of centrality or middle of the distribution. Let's look at some examples. First of all, I think it'd be pretty clear from this one that 5 is going to be our best value of the middle, symmetrical distribution. However, as we move to a negatively skewed distribution, then it becomes less clear where the exact middle is. Is it at this peak, or is it more to the negative side of that peak? We can also have here what is a bimodal distribution, where instead of having just one peak, which is what we assume we're going to see most of the time, it's not a guarantee. Sometimes we can see bimodal or even multimodal beyond just 2 peaks in a distribution. So normally we like to assume we have normally distributed, we'll keep talking about what that means in future chapters, and symmetrical or close to symmetrical data, but we actually have to look at it before we can believe that assumption has been held true. And we have three primary measures of central tendency: the mean, the median, and the mode. Again, I assume most of you have already been familiar with these concepts, at least to some extent, in your regular life and also in class and school. First of all, let's look at the mean. This is very simply an average. So we add up all the scores and then divide by the number of scores. We have a couple new notations to keep in mind. First of all, we have our population value. Our population notation is a mu, which is this little italicized and funky looking U. That is our population mean, again pronounced mu. And then big M, capital M italicized, is our sample mean. Let's look at our equations then. We have our equation for a population mean, again using our mu, big N for population size. And then we have our formula for our sample mean, which is big M for sample mean, and then little n to represent our sample size. Big N, population size; small n, sample size. Mu, population mean; big M, sample mean. Notice our sigma x is the same for both our population and our sample mean equations. Let's think about some maybe exceptions or other ways to think about the mean. It is if we have a certain number of units, or in this case, a certain number of students, and a total, in this case, money. If we have an average, each person would get the exact same amount. So you can see if we had 26 students in class and we had $1,000 to divide, we can see, I would have to check this math again, that doesn't look quite right. Maybe let's see, we had 9 students in the class. But we think about it in terms of moving to maybe a little bit better example now that I'm looking at it, the balancing point for the distribution. So for example, if we think about it as a balance, where underneath this whole set of scores do I move this slider so that this actually balances? And you can see these values close to where this middle point is going to be kind of bunch up, but have to take into account more the effect of outliers. So outliers, as we can see visually, tend to have a bigger effect on the mean, and the more of an outlier we make them, the more we have to adjust the mean to account for even just that one score, even if none of the other scores have changed. One thing to keep in mind is the idea of a weighted mean. So let's say we wanted to calculate a mean that involved multiple groups. So in this case, these groups have uneven sample sizes. So in this case, we have a sample size of 10 people in group 1, 4 people in group 2, and we have 2 means. What's the total mean? You may think we can just take these 2 means of these 2 groups and then just divide by the number of groups. But if we add these up, 150 divided by 2, the total mean is not 75. Why is that? Well, think about the sample size. If these sample sizes were equal, 10 and 10, then we could just do our 2 means divided by 2, and that would be the correct answer. But since these are different sample sizes, we see that we are over-representing the importance of this smaller sample mean if we just divide by 2. So instead of looking at our means of our 2 groups, we have to go backwards. In this case, we have to go backwards to our sigma x for group A, sigma x for group B, and then we can use that value for our weighted mean. So again, for 10 people, our sigma x would have to equal 10 people times our mean of 50. That's just working backwards through our mean equation. Same thing applies here. We're just working backwards through our mean equation. We know our sample mean is 100, and that equals sigma x over 4. So that means our sigma x has to equal 400. And now we see, because these are different sigma x's, that why it would have been appropriate inappropriate just to average these two means with uneven sample sizes between the groups. So now we can see our new mean corrects in that this sample is smaller. We don't want to over-represent the influence. We can see by a 75. Now if we go back to our sigma x for our weighted mean, now we see a mean that is more close to our mean with our larger sample group. Couple more ways to think about the mean. What happens if we add a score or change a score or take away a score? Well, this, if we go back to the balancing analogy, changes where the balance point is going to be. So for example, if we have 20 students and the mean is 77%, but we have student number 23 got a very low score because she was sick, and getting a retest replaces one score out of these 20 from a 37 to a 98. How will the class mean change? Well, take a low score, change it with a really high score relative to the average, and that average is going to go up. What if there were 200 students? Well, here's where we see the importance of sample size. 200 compared to 20 students, changing one mean has less of an effect. Now, one thing to keep in mind is that if we factor in a constant, which is to every score, we either add or subtract the same value, which is a constant. The same value affects everybody equally. As an example, for extra credit, 3 points to every score. Everybody got the extra credit right. So that's a constant in this case because everybody gets the same addition of 3 points. We would see that that is going to increase the mean by 3. Multiplying or dividing by the constant does the same thing to the mean. So we can convert into units of percentages, into proportions, or into units of 100 points to 1,000 points. Multiplying by a constant, if we do that to each individual score, has the same effect as if we multiply that mean or divide that mean. Now let's look at another measure of central tendency, which is the median. This is the score that divides the distribution in half. So that for whatever our m size, divide that by 2. Whatever that middle score is going to be the median. And we see here's the clearest example, 5 scores, 1, 2, 3, right in the middle, 2 below, 2 above. This one score is clearly the median. This works best once we have an odd number of scores for our sample size, but not that difficult to incorporate if we have even number of scores either. So let's look at a couple quick examples. What is the median for this first set? It will be 4, the score exactly in the middle. Now next we're having distribution with a lot of outliers in terms of a very low value, some very high values, but we count the number of values, 7, and then 1, 2, 3, 4. That middle value should be our median score. And finally, now we have an n size of an even number, and here we see the n is 6, and we count to, we don't have one score that's right in the middle, so typically we take these values and have to incorporate both of them. So in this case, we would just add these two middle values together and then divide by 2. So the set 3 is a little bit more complex. I think for our purposes, as long as we just cover conceptually that what the median represents, even with an even sample size, is still the very middle of the set of scores. So that basic concept doesn't change, and so the median we interpret the same way, whether it's an even set of scores or an uneven set of scores. Couple more things to consider between the median and the mean. First of all, if we have the following set of scores, this is a big outlier. If we use all these scores in our sigma x for our mean equation, we're going to see that this 140 really brings the mean up compared to the rest of the scores. If we just considered these, the mean is somewhere around here. Now, what the mean does, what the median does compared to the mean is still, if we calculated the median, what would our value be here? Our value would be the one right in the middle. So in this case of scores with extreme outliers, the value we get for our median is too influenced by this one big one. And the median, instead, we get for 3, which looks a little bit better for this set of scores. Now, in practical senses, what do? We want to look at this score, and if we have this set of numbers, we can't use the mean because it's going to be too biased toward this outlier. So then we have to think about, is this outlier real? If it is a real important number, then we have to include it. We have to consider it. On the other hand, if it's, for example, an error in measurement, an error in entering the data, we may just want to get rid of this outlier, go with this set of 6 scores instead. We think these are really valid measures. This one wasn't. It was just an accident, or we can explain it away in another reasonable way. Then with these 6 scores, we could justify using the mean. But if we had to use all 7 of these, the median would be the more appropriate measure of central tendency. And finally, let's look at the mode. What is the mode? This is the one score that occurs most frequently. So for example, if the mode is the most frequently occurring score, I think this F, our frequency of scores, frequency of individual scores, will help us with the mode. In this case, the X value with the highest frequency is X equals 6, which has 5 X equals 6 values, and so that should be our mode, X equals 6. The important thing to keep in mind too is that typically with our mean especially, we often think about that going with our continuous levels or scales of measurement. So our continuous variables, either interval or ratio, where the intervals are equal at the very least. The mode can be used with all scales of measurement. So certainly if we're comparing types of burger chosen, whether it's a chicken sandwich versus a double cheeseburger versus a burrito, the mode can tell us which one has the highest value, which one was most frequent in a given sample or population. So for example, this would be ordinal level data because we know seniors have more credits than juniors, but some seniors have only a couple more credits than someone who's characterized as a junior. Some seniors have 30 or more credits than someone who is classified as a junior. So it is ordinal but not continuous level data, but we see the mode can be clearly used here with this class in college classification, and we see the mode for this would be freshman standing. Wasn't looking at the entire set of scores, so the mode here would be the one with the highest frequency, and there are the most freshmen in this sample, and that's what the mode is, 66. Going back to our previous example here. Actually, no, this isn't our previous example. The numbers have changed a little bit. We still have X of 1 through 10 individual potential values, and here's the frequency of all these. What is the mode here? Well, we see there's not one X value with the highest frequency. We actually have 2 X values with the highest frequency. So this would be a bimodal distribution. There are 2 modes, X equals 9 and also X equals 3. What do we see about the following set of scores? One thing that this shows us is that the mode, we just find the number that has the highest frequency, in this case 3. It really has nothing to do with the outliers at all. So outliers can be present and we can still calculate the mode, and that's not really going to be biased or influenced by the presence of extreme outliers or not. Now, if we think about the shape of this distribution, what is it going to look like? It is positively skewed because most of the values are on the left side, but that extreme high value is going to pull the mean toward the right or in the positive direction. What is the most representative measure of central tendency? Well, in this case, it would not be the mean because of the extreme outlier. And we can see if we calculate the exact values, here we see the median and the mode are the exact same thing. That's not always the case, but they tend to stick together more closely when we have non-symmetrical data. Although the mean certainly is far from, the mode, is far from perfect, because in this case we have a mode of 85. This is the most frequently occurring score, although this value, I would say, is not the most representative of the entire set of these numbers. So in this case, what's the most representative measure? Probably the median, because our mode is biased a little bit, and we know that our mean is also going to be heavily influenced by these high scores and further away from what most of the scores generally are around. And we can see the actual values. We see the median is closest to the most common, or the common set of scores or spread of scores, 1 through 9, and then the mean is the most, the mean is a little biased, certainly from that 1 to 9 of most of the majority of the scores, and then the mode, of course, since they're all at the very highest value, really is furthest away from what we would consider of the best central tendency in terms of the basic goal of central tendency. So sometimes you just have bad data and none of them are great. In this case, we would like to use the mean, but with those outliers we can't, so the next best is going to be the median for this set of scores. We've talked about some of these classifications and considerations, but we want to use the mean for the most part, and here is a very important point. Because the mean includes the value of every score in the distribution. That's going back to our sigma x that's used to calculate it. We also, in the next discussion of what do we do next in terms of building our foundation blocks of statistical tests, we have the concepts of variance and standard deviation, and to get these we have to use the mean. We'll introduce those formulas in another narrated slideshow. So a lot of our fundamental pieces of doing statistics involve the mean. So we're going to try and be able to use that if we can, whenever possible. When might we use the mode? When we're dealing with discrete data, either a nominal or ordinal scale. Sometimes if the data is really skewed, it's not appropriate to use a mean, as we've talked about. Extreme outliers, and other cases where it may not make sense to use the mean. So if we do have skewed distributions and extreme scores, typically the median is what we default to next, the next best. If we have open-ended distributions for which they're, for example, time to complete a test, if you don't set a time limit on it, somebody could take however long, theoretically, infinity time to complete that test. In that case, the mean would be inappropriate. A lot of times, though, we would maybe put an artificial cap on this and pretend that it does have a cap on the distribution. But if we're going to be a data purist, if it is an open-ended distribution, we should not use the mean. And of course, if we have ordinal data, we can't use the mean, so we have to use the median instead. So now let's look at our distributions in terms of the shape of the distribution and what happens to the mean, median, and mode. So the first one is our ideal scenario where we have a symmetrical distribution, and look at this. Our mean, median, and mode all pile up right at the center, right in the middle. They're all the same value. Once again, symmetrically distributed data gives us the clearest explanations, the clearest presentation of the data. There's no noise to work with here. Now we can have our bimodal distribution. So there are two peaks in this set of data, so two modes. The mode's always at the top of the peak, but the actual average and then the middle value, the mean, are going to be in the middle. And we can have a distribution with no peak. And if there's no peak, there is no mode to be calculated. But then again, the mean and the median would be here at the middle and would be, if we can't use the mode, that's okay because we'd prefer to use the median with this set of scores anyway. Now, if we do have a set of scores like this with no peak, we can't assume that we're working with what we'll call normally distributed data. So we can't just pretend that this situation is as good as this situation for running our statistical analyses. But in some ways, we can use the mean and the median. It's a little bit better than bimodal data. But again, we're looking for something that approximates this for most of the statistical tests that we're going to use. And if we have data that looks like this, the mean, median, mode are all about the same, we're going to choose to use the mean, and then we can calculate our variance and standard deviation. And then we have our pillars, mean and standard deviation, upon which a lot of our further statistics are going to be based on. And then we have our last view of distributions and how different distributions affect differences in our measures of central tendency. So for example, if we have our classic positively skewed distribution, been talking about this a lot, but here's our last chance to see it. We have our data bunched to the left side of our frequency distribution. The peak is always going to be where the mode is. The median gets pulled a little bit in the positive direction, and then the mean gets skewed or pulled the most in the positive direction. The same thing, but opposite, happens when we have a negatively skewed distribution. The peak is on the right side, or in terms of higher values than the middle, and then our median is pulled lower than our mode, and our mean is pulled even further in the negative direction from the mode in our negatively skewed distribution. So I hope that's a good review and maybe introduced a few new things for you to consider in terms of thinking about central tendency, and as we move forward specifically and incorporate measures of central tendency, specifically the mean, into the statistics that I think are going to be more interesting, a little bit more complicated, but more fun. So lots of things to consider, even from this very simple conceptualization of data. So looking forward to discussing this and more in the discussions.